For the last several million years, Earth's climate has moved in cycles, not slowly drifting, but repeating. Ice ages came and went. Sea levels rose and fell by hundreds of feet. These shifts left clear signatures in ice and stone. What puzzled scientists wasn't that the climate changed, it was why the timing was so precise. Again and again, the same intervals appeared, not once, not twice, but across continents, oceans, and thousands of miles of ancient records. The planet seemed to be responding to something steady, something patient, something far removed from storms, volcanoes, or human influence. The sun has remained mostly steady through these ages, yet Earth slipped in and out of cold and warmth as if following a schedule. Human civilization emerged during one of these rare warm intervals, a brief calm within a much longer pattern. Humans emerged during one of these rare warm pauses, building civilizations during a brief calm in a long, unstable cycle. But if Earth's climate follows a hidden schedule written into space itself, what does that say about the world we know? What if warmth is not the default state, but a short interlude between long ages of ice? How can motions that never touch the planet control ice, oceans, and life so completely? And if this cosmic pattern governs the past, where do we stand within it now? Tonight, we follow the quiet clues left in ice, stone, and sunlight. But before we begin, I'd love to know where in the world are you listening from tonight, and what time is it there? Your comments are one of my favorite parts of this sleepy little community. If you're enjoying these late night explorations, a like and a subscribe would mean a lot. And for those already subscribed, thank you for being part of this calm little corner of science. Now take a slow, deep breath, let your shoulders relax, and together let's drift into the hidden rhythms that have been shaping Earth's climate all along. Long before names existed for continents or skies, the planet moved through climates that would feel unimaginable today, not as sudden catastrophes, but as long decisions made by physics and time. Rocks that now rest in quiet deserts were once carved by ice, their surfaces scratched and polished beneath frozen oceans. Elsewhere, chemical traces locked in ancient stone show warmth spreading across latitudes that no longer know such heat. These signals appear far earlier than forests, far earlier than animals with backbones, recorded when life itself was still learning how to endure. There were moments when Earth nearly vanished beneath ice, oceans sealed under a global shell that reflected sunlight back into space. Even near the equator, glaciers advanced slowly, pressing into shallow seas where early microbes clung to survival. These snowball Earth episodes did not arrive once but returned, separated by long recoveries that unfolded across millions of years. When ice finally loosened its grip, the planet did not ease back into balance. Heat followed with intensity, greenhouse conditions spreading warmth rapidly as volcanic gases accumulated beneath newly opened skies. The swing from frozen silence to saturated warmth left chemical scars still read by modern instruments. Between these extremes, life adapted not through speed but persistence. Simple organisms learned to endure darkness under ice, then exploit sudden floods of nutrients when melting began. Photosynthesis reshaped the air during warming phases, slowly altering the chemistry that governed temperature itself. Climate and biology moved together, each responding to the other without intention, guided by feedbacks that had no awareness of the future they were creating. Evolution did not follow a steady slope upward, but bent and paused as environments tightened or loosened their grip. As ages passed, the planet rarely lingered in moderation. Warmth encouraged expansion, oceans spreading inland, while shallow seas bloomed with life. Cooling reversed that reach, pulling shorelines back and grinding landscapes into stone and dust. Each transition altered which traits survived, favoring flexibility over perfection. Stability was not a reward offered by the planet, but a brief alignment of forces, held only until something shifted again. By the time complex animals appeared, Earth already carried a long memory of change. The surface had learned how to freeze deeply and recover, how to overheat and settle again into quieter patterns. What later eyes would call balance was always temporary, a pause between larger motions. The climate before humans was not chaotic, but it was never still. It moved as Earth itself moved, slow enough to feel eternal, restless enough to shape every path life would later take. A single day passes like a ripple across water, brief and easily disturbed. Clouds gather, winds shift, rain arrives or does not, and by nightfall, the pattern is already gone. These daily motions feel intimate because they touch skin and ground directly, yet they vanish almost as soon as they appear. Weather lives in these fleeting moments, shaped by turbulence, chance, and local conditions that never repeat in quite the same way again. Over longer stretches, repetition begins to form a softer outline. When days, seasons, and years layer over one another, their sharp edges blur into something steadier. This is climate, a portrait painted not by any single storm or drought, but by thousands of them blended together. A region becomes known for warmth or cold, dryness or rain, not because every year behaves the same, but because the balance settles into a recognizable range. Climate carries memory, smoothing chaos into expectation, yet it still belongs to human timescales, measured in generations and records that fit within history. Beyond this lies a deeper movement, one that does not respond to decades or even centuries. Deep climate unfolds over spans so long they resist intuition, stretching across thousands and tens of thousands of years. Here, individual storms vanish entirely, and even familiar climates dissolve into larger transitions. Ice sheets grow and retreat, oceans expand across continents and withdraw again. Atmospheric composition slowly reshapes the way heat is held or released. These changes do not hurry. They proceed with a patience that makes them nearly invisible from the surface of everyday life. The difference is not simply duration, but scale. Weather is noise, a constant flicker of motion that masks any larger signal. Climate is the averaged rhythm beneath that flicker, something stable enough to name, yet still capable of change. Deep climate moves the frame itself. It alters the background conditions that define what climates can exist at all, determining whether ice can survive summers or whether warmth spreads poleward, unchecked. Human intuition evolved inside short windows, attuned to seasons and years, because those mattered for survival. Movements that span millennia leave no imprint on instinct or memory. A cooling trend lasting thousands of years feels indistinguishable from permanence when experienced only a few decades at a time. Each generation inherits a narrow slice and assumes it reflects the whole, yet the planet does not share this assumption. Deep climate continues regardless of observation, driven by slow forces that accumulate their influence grain by grain, photon by photon. What feels fixed is often only paused, balanced briefly between larger motions already underway. Understanding this difference does not require witnessing the full arc, only recognizing that Earth's most powerful changes arrive quietly beneath the threshold of immediate perception, shaping the stage long before anything steps into view. Long before air carried sound or oceans reflected light, energy began arriving from a distant surface of fire. It traveled quietly, crossing empty space until it reached a turning sphere, warming stone, stirring water, and setting motion into everything that could move. This steady arrival shaped day and night, guided winds and currents, and gave the planet its basic rhythm. Nearly every breath of warmth Earth has ever known traces back to that uninterrupted stream. Earth does not create heat on its own in any lasting way. Volcanic fires glow briefly, friction grinds mountains down, chemical reactions whisper warmth into small corners, yet all of these fade beside the influence of sunlight. From the gentle lift of evaporation to the slow storage of heat in oceans and soil, climate begins with how much solar energy arrives and where it settles. Without this input, the planet would drift cold and silent, locked beneath ice regardless of atmosphere or water. What makes this relationship remarkable is the steadiness of its source. Across the spans that shape ice ages and oceans, the sun's output changes very little. It brightens and dims over timescales far longer than those recorded in Earth's climate archives, too gradual to explain repeated swings between frozen and warm worlds. Chemical signatures in ancient sediments confirm this quiet consistency. The furnace remains lit at nearly the same strength while Earth itself experiences dramatic shifts. This creates a subtle imbalance between cause and effect. If the energy supplied remains almost constant, then the differences must come from how that energy is received. The climate system responds not only to quantity but to distribution, to where sunlight falls, how long it lingers, and which surfaces absorb or reflect it. Ice, water, rock, and air each interact with light differently, shaping pathways that amplify or soften its influence. Small redistributions can grow large when allowed to accumulate over long periods. Viewed from space, Earth appears calm, bathed evenly in sunlight as it turns. From within, the experience is anything but uniform. Seasons slide across hemispheres, ice advances or retreats, oceans store warmth and release it slowly, clouds scatter light back into darkness. All of this unfolds beneath a solar glow that barely changes, like a constant note supporting a shifting melody. The stability of the sun removes it as the conductor of climate's largest transformations. Instead, it becomes the quiet reference point against which other motions stand out. Something within Earth's relationship to that light is adjusting, redirecting energy in slow, precise ways that shape epochs. The power driving climate remains the same, but the manner of its arrival quietly shifts, allowing frozen worlds and warm intervals to emerge from a source that never wavers. Earth travels its path without leaving a mark, yet the shape of that journey is never fixed. From one age to the next, the planet's route around the sun gently reshapes itself, stretching outward, then easing back again, like a slow breath taken over tens of thousands of years. This motion is not a sudden deviation but a gradual adjustment, guided by gravity's quiet negotiations with neighboring worlds. The orbit is often imagined as a clean circle, simple and dependable. In reality, it is slightly oval, and that ovalness is not constant. At some times, Earth's path becomes more elongated, carrying it a little farther from the sun at one end of the year and a little closer at the other. At other times, the path grows more rounded, softening those differences until distance changes feel almost even across the seasons. The movement between these states happens slowly, far beyond the scale of human calendars. Though the change in distance is subtle, the consequences accumulate patiently. When Earth drifts slightly closer to the Sun during part of its orbit, sunlight arrives with greater intensity, not enough to be noticed in a single year, but enough to matter when repeated again and again. When it travels slightly farther away, that energy weakens just as quietly. Over thousands of years, these small imbalances shape how much warmth reaches the surface during critical moments of the seasonal cycle. This stretching and relaxing does not act alone, nor does it rush. It unfolds while oceans circulate, ice forms and melts, and continents continue their long drift. The orbit sets a background condition, a gentle modulation of distance that influences how sunlight is shared across time. It does not force immediate change, but nudges the system, allowing other processes to respond and amplify its effects. The enormity of the timescale hides the motion from ordinary perception. Generations pass without sensing any difference, while the orbit continues adjusting with precision. By the time the path has noticeably changed, landscapes have transformed, species have shifted, and coastlines have moved. The cause remains remote, its influence spread thinly across millennia rather than concentrated in moments of drama. Seen from afar, this orbital variation resembles restraint rather than power. The planet never strays far from its star, never risks escape or collapse. Yet within that narrow range, enough variation exists to matter profoundly. The climate responds not to dramatic leaps in distance, but to the patient repetition of tiny differences allowed to echo across deep time. Earth's orbit is therefore not a fixed track, but a slowly breathing curve, tightening and loosening without pause. Its movement is modest, almost humble, yet it carries the weight of ages. In that gentle reshaping lies one of the quiet mechanisms through which light, distance, and time combine to guide the planet's long climatic story. Sunlight does not arrive as a solid presence, but as a stream that thins with distance, spreading itself across space before touching the planet. When Earth moves slightly closer, that stream concentrates just enough to leave a trace. When it drifts slightly farther away, the same light stretches thinner, losing a fraction of its strength. These differences are delicate, almost invisible in any single moment, yet they never vanish entirely. They settle quietly into the planet's surface, one season at a time. The effect is not about dramatic heating or cooling from year to year. Instead, it appears in how summers and winters distribute energy across latitude and time. A small change in distance can tilt the balance of a season, allowing summers to deliver slightly more warmth or slightly less. On their own, these differences fade quickly, but when repeated across thousands of years, they begin to matter. Seasons stack upon seasons, each one adding or subtracting a thin layer of energy from the system. Ice responds with patience. It does not react to a single warm summer or a single cold winter. It listens to averages, to patterns sustained long enough to overcome its own inertia. When summers grow marginally weaker over many cycles, ice persists longer each year, surviving melts that once erased it. Snow accumulates more easily, compressing into ice, brightening the surface and reflecting sunlight back into space. Cooling deepens not because distance changed greatly, but because ice remembers every small shortfall in warmth. When distance favors slightly stronger summers, the response unfolds just as slowly. Ice retreats a little farther each year, exposing darker ground and water that absorb more sunlight. Melt seasons lengthen, and accumulated heat begins to outweigh the memory of cold. This shift does not rush. It proceeds through countless seasonal adjustments, each one modest, each one contributing to a gradual rebalancing. Over long spans, these tiny changes in sunlight distribution reshape entire regions. Ice sheets thicken or thin, sea levels respond, and atmospheric circulation adjusts to new contrasts between reflective ice and absorbing land or ocean. None of this requires a dramatic change in the sun itself. It emerges from geometry and repetition, from the quiet arithmetic of distance multiplied by time. The key lies in accumulation. Climate is not governed by peaks but by persistence. A small difference, sustained long enough, becomes significant simply because nothing interrupts it. Earth absorbs, stores, and releases energy with great delay, allowing weak signals to gather strength through continuity alone. In this way, distance alters climate not by force but by consistency. The planet responds to the long conversation between light and surface, written slowly across ages. What seems negligible within a lifetime becomes decisive across millennia, guiding ice and warmth through a story shaped by patience rather than scale. Earth turns through space with a quiet lean, never fully upright, never perfectly aligned with its path around the sun. This gentle inclination is not visible from the surface, yet it is written into every sunrise and every shifting shadow. The planet rotates as it always has, but its axis carries a persistent angle, a subtle refusal to stand straight that shapes the rhythm of light across the globe. Because of this tilt, sunlight does not fall evenly throughout the year. One hemisphere inclines toward the sun, receiving longer days and higher arcs of light, while the other leans away, passing through shorter days and shallower warmth. Months later, the roles reverse. Seasons emerge not from changes in the sun itself, but from how Earth presents its surface to that steady glow. Summer and winter are born from geometry, from orientation rather than intensity. The tilt defines contrasts. It creates polar regions that experience long nights and long days, and equatorial zones where light remains more evenly shared. Ice forms or melts according to these patterns, responding to how long sunlight lingers rather than how bright it burns. Winds and currents adjust as temperature differences shift between hemispheres. Life organizes its cycles around these slow oscillations, timing growth, migration, and rest to the predictable swing of exposure and shadow. Yet this angle is not locked in place. Over very long spans, the tilt itself drifts. The axis gently shifts its inclination, becoming slightly more pronounced at some times, slightly more restrained at others. These changes happen far too slowly to notice within a lifetime, unfolding across tens of thousands of years. Still, their influence accumulates, quietly modifying the contrast between seasons. When the tilt grows stronger, seasonal differences sharpen. Summers deliver more direct sunlight, winters retreat further into darkness. Snow and ice feel these changes deeply, responding to prolonged warmth or extended cold. When the tilt softens, seasons mellow. Extremes ease, and the distribution of sunlight becomes more even through the year. Neither state is permanent. The planet passes between them patiently, guided by gravitational interactions that never hurry. This slow variation does not act in isolation. It interacts with distance, with timing, with the reflective surfaces of ice and cloud. The tilt determines how energy is spread, which latitudes receive surplus warmth, and which surrender heat back into space. Over many cycles, these small adjustments influence whether ice survives summer or succumbs to melt, whether cold expands or retreats. Earth's axis therefore carries both stability and change. The basic tilt remains, sustaining the familiar structure of seasons, yet its gradual variation introduces long waves beneath that surface rhythm. Climate responds not to a single summer or winter, but to the cumulative pattern shaped by this quiet leaning. The planet continues to turn, inclined just enough to matter. That inclination drifts slowly, almost imperceptibly, yet it guides the long balance between light and darkness. In this steady motion, seasons are renewed, and over deeper time, climates are gently steered without urgency or pause. Seasonal contrast is not fixed, but breathes subtly with the planet's posture. As Earth's tilt increases, The swing between light and shadow deepens across the year. Summers receive sunlight that climbs higher and lingers longer, while winters withdraw into extended dimness. The change is gradual, unfolding across spans that outlast memory, yet it reshapes the balance that governs heat and cold at the surface. When the tilt grows stronger, sunlight concentrates more sharply into summer months. High latitudes receive a greater share of that energy during brief intervals, allowing warmth to penetrate surfaces that otherwise remain frozen. Ice responds to duration rather than intensity alone. Extended summers give melting more time to work, thinning ice from above and loosening its hold on the ground beneath. Rivers lengthen their flow, soils warm more deeply, and reflective surfaces give way to darker ones that absorb light more readily. Winter follows with equal resolve. Stronger tilt draws the sun lower or away entirely, allowing cold to persist. Snow accumulates more easily when long nights dominate, and fresh layers brighten the landscape, sending sunlight back into space once the season turns again. The planet holds both extremes at once, with summers that challenge ice and winters that reinforce it. The outcome depends on which side gains more ground across many cycles. As the tilt eases, the contrast softens. Summers lose some of their reach, delivering warmth more gently and for shorter spans. Winters, though still cold, retreat from their most severe expressions. Snow and ice feel this moderation immediately. Melting becomes less decisive, and winter accumulation faces fewer extremes. Ice sheets respond by stabilizing, neither driven rapidly toward growth nor pushed strongly toward retreat. The surface settles into a quieter exchange with sunlight. These shifts guide ice not by command, but by consistency. A single mild summer or a single harsh winter matters little. What matters is repetition, the patient stacking of seasons that lean in the same direction. Over thousands of years, slight advantages compound. Ice grows thicker when summers repeatedly fall short of clearing it away. Ice thins when summers regularly extend just long enough to undo winter's work. The process leaves marks that linger. Growing ice reflects more light, reinforcing cooling. Shrinking ice exposes darker ground and water, allowing warmth to persist. In this way, tilt shapes not only seasons, but feedbacks that amplify small differences into broader change. The planet listens to these signals without urgency, adjusting slowly to the balance presented year after year. Seasonal strength, then, becomes a quiet regulator. It determines whether ice advances cautiously or retreats step by step. Within this slow modulation, climates drift between states, guided not by sudden force but by the long patience of geometry. The seasons continue their measured exchange, growing stronger or weaker as Earth's tilt gently shifts, shaping the frozen and thawed contours of deep time. Ice accumulates without urgency, layer settling upon layer, each one preserving a faint record of the conditions that allowed it to remain. Snow falls, compresses, and hardens, locking air and dust inside a growing archive. This process does not judge a single season. It responds to patterns that repeat often enough to matter, storing the outcome quietly until the surface itself begins to change the fate of light. As ice spreads, it alters the planet's appearance from above. Bright surfaces reflect sunlight outward, sending a portion of incoming energy back into space before it can warm air or ground. This reflection does not require motion or force. It happens instantly, silently, whenever light meets ice. The effect is subtle in isolation, yet extensive when ice blankets large regions. Cooling deepens not because more energy leaves the sun, but because less of it remains behind. The presence of ice encourages its own persistence. Cooler temperatures favor snowfall over rain, extending the conditions that allow accumulation. Longer lived snowfields brighten the surface further, reflecting even more light. Each season reinforces the last, not through speed but through continuity. What began as a small advantage gradually reshapes regional climates, lowering temperatures enough to invite further growth. Ice remembers every year that favored its survival, and that memory thickens with time. When ice begins to retreat, the memory fades just as gradually. Melting exposes darker ground and open water, surfaces that absorb sunlight rather than return it to space. The same energy that once glanced away now lingers, warming air and soil, lengthening melt seasons slightly. These small gains accumulate, weakening ice from below and above. Retreat rarely happens all at once. It proceeds through repeated summers that deliver just enough warmth to undo winter's contribution. The contrast between ice and its absence creates powerful feedbacks. Growing ice cools the planet further by altering how energy moves through the system. Shrinking ice allows warming to persist by reversing that exchange. These feedback loops do not operate independently of other forces, but they amplify them. A small nudge becomes more influential once ice responds because the surface itself begins to participate in the outcome. This is why climates can settle into prolonged states. Once ice sheets reach a certain extent, they stabilize conditions that favor their continuation. Once they recede beyond a threshold, warming becomes easier to maintain. The system does not forget quickly. It carries forward the consequences of past seasons, embedding them into geography and energy flow. Ice, therefore, serves as more than frozen water. It is a physical memory of climate, holding the imprint of long patterns that shaped its growth or retreat. Through reflection and absorption, it translates history into present conditions. Within these feedbacks, Earth finds ways to linger in cold or warmth, not because change has ceased, but because memory has taken hold, guiding the planet gently along paths carved by repetition and time. The direction Earth faces does not remain fixed against the distant stars. Over immense stretches of time, the planet's axis slowly traces a wide, graceful circle, turning its orientation almost imperceptibly. This motion unfolds so gradually that it leaves no trace in daily experience, yet it quietly repositions the planet's posture in space, altering how sunlight meets the surface across ages. As the axis shifts, the timing of seasons drifts with it. The familiar cycle of summer and winter continues, but their placement within the orbit subtly changes. One hemisphere may experience summer when Earth is slightly closer to the Sun, while thousands of years later, that same hemisphere receives summer light when the planet is slightly farther away. The amount of sunlight does not change dramatically, yet the alignment between season and distance does, and this timing carries weight. This slow turning resembles a clock hand moving across a dial that cannot be seen. Each position favors a different arrangement of light across hemispheres, adjusting how warmth is distributed through the year. Summers may grow slightly more effective at melting ice in one era, then gradually weaken in another, not because of changes in the sun, but because of when those seasons occur along Earth's path. The wobble moves with patience. It requires many thousands of years to complete a full circuit during which coastlines shift, species migrate, and ice advances or recedes. Through it all, the axis continues its steady motion, realigning the calendar of seasons relative to orbital position. This creates long waves of influence, subtle enough to escape immediate notice, strong enough to matter when layered across deep time. Ice responds to this timing with sensitivity. Melting depends not only on summer warmth, but on when that warmth arrives. Summers aligned with closer approaches to the sun carry a slight advantage, delivering energy when it can do the most work. When alignment shifts the other way, summers lose some of that efficiency. Over repeated cycles, these differences guide whether ice persists or retreats, not abruptly, but through accumulation. The atmosphere and oceans follow along, adjusting currents and circulation to new contrasts between hemispheres. Winds shift gradually, heat storage changes, and the rhythm of seasons takes on a slightly different emphasis. Nothing breaks or resets. The system adapts continuously, responding to the slow redrawing of celestial geometry. This wobble adds another layer to Earth's long story, a quiet rearrangement rather than a disruption. It does not override the effects of tilt or distance, but weaves them together, adjusting their impact through timing alone. In doing so, it contributes to patterns that repeat without ever being identical. Earth continues to turn, leaning and drifting in orientation with a calm persistence. The seasons keep their names, yet their deeper relationships evolve, guided by this slow circular motion. Through it, light finds new pathways across the planet, and climate follows, shaped once again by movement too gentle to feel, yet too steady to ignore. Warmth does not act on ice simply by arriving, but by arriving at the right moment. Throughout Earth's long history, glaciers have cared less about how cold winters became and far more about what summers failed to undo. Snow can pile high during dark months, yet if summer light lingers long enough, that accumulation quietly disappears. Timing, not intensity alone, decides which side of the balance holds. Winter builds ice patiently, snow falls, settles, and compresses, adding mass that waits beneath dim skies. This process feels powerful because it is visible and persistent, but its work remains provisional. Ice formed in winter carries an unspoken condition that it must survive the following summer to matter. Without that survival, winter's effort fades like a footprint in thawing ground. Summer operates differently. It does not need to be extreme to be effective. It only needs to last long enough and arrive when ice is most exposed. Melting requires sustained contact with sunlight, hour after hour, day after day. A brief surge of warmth means little if nights remain long or angles remain low. Ice listens to duration. It yields only when warmth persists past a quiet threshold. This makes seasonal timing decisive. When summers align to deliver their warmth at moments of greatest exposure, melting gains ground. Ice thins from the surface, loses reflectivity, and becomes easier to warm in subsequent years. When summers arrive slightly misaligned, when warmth peaks earlier or later than ideal, ice survives despite similar average temperatures. Over thousands of years, these differences accumulate, guiding the slow rhythm of advance and retreat. Glaciers therefore grow not because winters are especially harsh, but because summers repeatedly fail to erase their growth. Retreat begins not when winters soften, but when summers consistently exceed what ice can endure. This asymmetry shapes the pacing of ice ages. Growth stretches across long spans, reinforced season after season, while retreat can unfold more quickly once timing shifts in favor of melt. The planet responds to these patterns with quiet precision. Ice margins creep forward when summers fall just short. They pull back when summers cross a narrow line, often unnoticed at human scales. Oceans, atmosphere, and surface follow suit, adjusting slowly to the changing presence of ice. Sea levels respond, winds adapt, and energy flows shift as reflective surfaces expand or shrink. Strength still matters, but only within the frame set by timing. A slightly warmer summer, placed correctly within the orbital cycle, can outweigh centuries of cold accumulation. Conversely, severe winters cannot overcome a sequence of summers that steadily dismantle ice. The system favors persistence over extremes. Through this lens, climate change across deep time appears less like a contest of force and more like a schedule carefully kept. Light arrives, not dramatically, but consistently, and ice responds only when conditions align just so. Glacial histories are written in calendars rather than thermometers, shaped by the quiet authority of when warmth arrives and how long it is allowed to stay. Far beneath the quiet surfaces of ice sheets, time rests in compressed layers, untouched by wind or sunlight. Snow that fell long before coastlines took their present shape has been buried, pressed into crystal, and sealed away from the living world. In these depths, ice becomes more than frozen water. It becomes a continuous record, preserved with a care that few other materials can match. As snow accumulates year after year, it traps tiny pockets of air before transforming into solid ice. These bubbles remain intact, isolated from the atmosphere above. Within them lingers a sample of ancient skies, held exactly as they were at the moment of burial. Oxygen, carbon dioxide, and other gases persist in their original proportions, allowing scientists to glimpse atmospheres that vanished long ago. Each bubble is a breath from a distant world, unchanged by everything that followed. The ice itself carries structure. Seasonal snowfall leaves, subtle differences in texture and chemistry, forming layers that repeat in recognizable rhythms. Summer snow differs slightly from winter snow, and those differences remain visible as alternating bands when cores are brought to the surface. By reading these layers, researchers can trace cycles of warming and cooling that unfolded long before memory or writing. Temperature shifts reveal themselves through isotopes locked into the ice, variations so slight they require precision to detect, yet consistent enough to map patterns stretching back hundreds of thousands of years. These cores do not tell a single story all at once. They must be read slowly, centimeter by centimeter, translating depth into time. Near the surface, layers are thick, reflecting recent centuries. Deeper down, they compress, time narrowing as pressure increases. Even so, continuity remains. There are no gaps, no missing chapters, only a steady accumulation that preserves the passage of years with remarkable fidelity. Across different regions, ice cores echo one another. Signals found in polar ice align with changes recorded in distant sediments and stone, confirming that the shifts they capture were global rather than local. Warming and cooling repeat in recognizable intervals, appearing again and again as depth increases. These patterns reveal that Earth's climate has rhythm, shaped by forces steady enough to leave their imprint repeatedly across deep time. What makes these clues powerful is their independence. The ice was not created to record history. It simply accumulated according to physical law, responding to snowfall, temperature, and gravity. Its testimony carries no interpretation, only preservation. Modern analysis brings meaning to what the ice has patiently held. Through these frozen layers, scientists found confirmation that climate changes followed regular pacing rather than random upheaval. The ice revealed cycles that rose and fell long before human influence, unfolding with a consistency that pointed beyond oceans and continents. In silence and darkness, the ice kept its memory intact, waiting until tools and curiosity were refined enough to listen. Far below the shifting surface of the ocean, particles descend without pause, settling into stillness once they reach the seafloor. Dust blown from distant continents, minerals washed from rivers, Shells formed by microscopic life all drift downward and come to rest. There is no rush and no interruption. Year after year, layer after layer gathers, building a quiet archive across basins that never fully empty. Unlike ice or stone, ocean sediments accumulate in constant dialogue with the climate above them. Warmer waters change which organisms thrive near the surface. Colder waters favor different forms, each leaving behind shells and fragments shaped by chemistry and temperature. As these remains settle, they carry information encoded in their structure, subtle variations that reflect the conditions under which they formed. Over time, the seafloor becomes a wide ledger, its pages written by biology and physics together. The chemistry within these sediments deepens the record. Ratios of oxygen isotopes locked into shells shift depending on water temperature and global ice volume. Trace elements respond to nutrient supply, circulation, and the balance between evaporation and rainfall. Nothing announces itself as a dramatic marker. Instead, meaning emerges through comparison, the way one layer differs from those above and below. Each difference holds a piece of a broader pattern. Sediments thicken slowly, compressing earlier layers, but rarely erasing them. Even after millions of years, continuity remains. Drilling into the seafloor reveals this persistence. Long columns of material rising from the deep, like extended memories, brought briefly into light. These cores do not rely on a single location. They appear across oceans, retrieved from different depths and latitudes, each one shaped by local conditions yet connected through global processes. When records from distant seas are compared, coherence begins to surface. Temperature signals rise and fall together, even when continents lie far apart. Changes seen near the poles echo in equatorial regions, adjusted in magnitude but aligned in timing. This consistency confirms that climate shifts were not isolated events but planetary movements, expressed differently depending on geography, yet governed by shared forces. Ocean sediments also extend further back than many other archives. They capture climates that predate extensive ice sheets, preserving evidence from eras when warmth dominated or cooling began its first slow descent. In these depths, the long cadence of Earth's climate becomes visible, repeating oscillations layered across ages that dwarf human history. The strength of this archive lies in its quiet reliability. The seafloor does not react quickly. It responds slowly, smoothing short disruptions and preserving sustained change. Storms leave little trace. Centuries blur together. What remains are signals that lasted long enough to alter oceans themselves. Through sediments, Earth's climate story gains scale and depth. Patterns emerge not from one place or moment, but from convergence across continents and seas. The ocean floor keeps its record patiently, holding evidence of ancient temperatures and shifting balances, waiting beneath the waves as another steady witness to time. In the early 20th century, far from ice sheets and drilling rigs, a mind turned patiently toward geometry and the sky. While others focused on storms, oceans, or the chemistry of air, Milankovitch worked with angles, distances, and time. His tools were equations and star charts, his setting a desk rather than a field site, yet his attention remained fixed on Earth and on the quiet regularity beneath its changing climate. Milankovitch approached climate as a problem of calculation. Trained in mathematics and engineering, he trusted what could be derived from first principles. He studied how Earth moves through space, how its path stretches and relaxes, how its axis leans and slowly turns. From these motions, he calculated how sunlight would be distributed across latitudes and seasons, not for years or centuries, but across spans that matched the rise and fall of ice ages. His work unfolded as a long exercise in precision, tracing how small astronomical changes might accumulate into planetary consequences. What made his approach unusual was its independence from direct observation. He did not rely on temperature records or historical accounts. Instead, he calculated climate using celestial mechanics alone, letting geometry dictate the outcome. In doing so, he proposed that the pacing of ice ages could be predicted by orbital variations long before physical evidence firmly linked the two. The climate, in his view, followed a schedule written in space. At the time, this idea found little traction. Climate science was fragmented, divided among disciplines that rarely spoke the same language. Geologists focused on rocks, meteorologists on weather, astronomers on stars. Milankovitch's work fell between these worlds, mathematical where others expected physical measurement, abstract where direct causation was sought. Without immediate proof, his calculations seemed distant from the messy complexity of Earth's surface. There was also the matter of timing. The tools needed to test his ideas did not yet exist. Deep ice cores had not been recovered, ocean sediments were still largely unexplored, and dating techniques remained imprecise. Without long records to compare against his predictions, his theory hovered without anchor. It asked for patience in a scientific culture accustomed to shorter cycles of validation. Milankovitch continued regardless, refining his calculations year after year, assembling a framework that connected orbital motion to climate response. He mapped how sunlight would vary at different latitudes through time, focusing especially on summer energy in high regions where ice persisted. His confidence rested not on a claim, but on internal coherence. The numbers aligned, the geometry held, and the logic remained consistent. Only later, as independent archives emerged from ice and sea, did his work find its echo. Patterns he had calculated appeared quietly in the data, aligning with rhythms preserved far from his desk. What had once seemed detached grew grounded, revealing that a patient attention to space could illuminate Earth's deepest changes. Numbers replaced clouds, and angles took the place of storms. Climate, in this view, could be approached without stepping onto ice or lowering instruments into the sea. It could be calculated quietly, using only the motions of Earth and the steady presence of the sun. Geometry became the landscape, and time stretched wide enough for equations to wander through ages. Orbital mechanics offered a framework that did not depend on observation of weather at all. The paths of planets were already known with remarkable precision. Their positions, tilts, and cycles could be traced backward and forward across immense spans. By combining these motions, it was possible to determine how sunlight would fall across the planet, latitude by latitude, season by season, far beyond any written record. The calculation did not ask what the climate was doing. It asked what light was doing. From this perspective, climate emerged as a response rather than a cause. If sunlight shifted predictably, then ice and warmth would follow with equal patience. The equations tracked how summer energy rose and fell in high latitudes, where ice was most sensitive. They showed that small variations repeated reliably, creating long beats of excess and scarcity. No thermometer was needed. The climate signal was embedded in orbital rhythm itself. This approach was radical in its restraint. It avoided the complexity of atmosphere and ocean, setting those aside without denying their importance. Instead, it treated them as participants responding to a deeper schedule. The climate could be forecast in principle, not by knowing future weather, but by knowing future geometry. Sunlight became the constant input, Earth's motion the variable filter. Such calculations demanded faith in abstraction. At the time, there were few long climate records against which to test them. Ice cores were shallow, sediment archives incomplete, dating methods still developing. The theory moved ahead of confirmation, confident in mathematics while evidence lagged behind. It described patterns that could not yet be seen, predicting cycles that would only later reveal themselves clearly. This gap between idea and proof left the work suspended for years. Without direct data to anchor it, the calculations felt distant from lived reality. Yet they remained internally consistent. The same cycles appeared again and again, emerging inevitably from the math. The geometry did not change its mind. When evidence finally arrived, it did not overturn the theory, it aligned with it. Records drawn from ice and sea traced rhythms already mapped on paper decades earlier. What once appeared speculative became foundational, not because it adjusted to new data, but because the data rose to meet it. Calculating climate using geometry alone revealed that Earth's deep changes followed order, not accident. It showed that climate could be shaped by motions that never touch the surface, guided by distances and angles rather than winds and clouds. The theory waited quietly for its time, patient as the cycles it described, until the world caught up to what the math had already seen. Separate motions move through space on their own paths, each slow and precise, each governed by gravity rather than chance. For long stretches, they operate independently, nudging climate in different directions without obvious coordination. Then, across deep time, their rhythms draw closer, and coincidence begins to matter. What was once a collection of quiet influences becomes a combined signal. One motion reshapes Earth's orbit, stretching it slightly, then easing it back. Another adjusts the planet's tilt, sharpening or softening seasonal contrast. A third repositions the axis itself, sliding seasons forward or backward along the orbital path. Each change remains small on its own, barely noticeable in isolation, yet none of them exists alone. All continue simultaneously, moving through cycles that sometimes drift apart and sometimes converge. When these cycles align, their effects overlap rather than cancel. A more elongated orbit can coincide with a stronger tilt, delivering increased summer energy to regions already primed to receive it. At the same time, the slow wobble can place that intensified summer precisely where distance favors additional warmth. The result is not a new force, but a concentration of influence, light arriving with better timing, for longer and where it matters most. At other times, the same cycles interfere. One may strengthen while another weakens, blunting the overall effect. A favorable distance might be offset by a muted tilt, or precise seasonal timing might arrive during a gentler orbital phase. Climate responds accordingly, easing into stability rather than change. These periods leave quieter marks in the record, moments when ice neither advances decisively nor retreats with urgency. The interplay between these motions introduces complexity without randomness. Patterns repeat, but not identically. Each alignment produces a slightly different outcome, shaped by which cycles reinforce one another and which resist. Ice sheets feel these differences acutely. Growth accelerates when multiple influences lean toward cooling. Retreat gains momentum when warming signals coincide across cycles. Over tens of thousands of years, this overlap explains why climate shifts arrive unevenly. Some transitions build slowly, supported by partial alignment. Others cross thresholds more abruptly when cycles synchronize more closely. The planet does not flip states suddenly. It is guided across boundaries by cumulative agreement between these motions. This convergence also explains why no single cycle dictates climate on its own. Distance matters, tilt matters, timing matters, but their true power emerges through combination. Climate becomes the sum of their relationships rather than the expression of any one. The system remains sensitive, yet constrained by geometry and repetition. As the cycles continue their silent progress, alignment appears and fades again. The process never settles into permanence. Earth moves through overlapping influences that alternately reinforce and restrain one another, shaping long arcs of cold and warmth. Within this layered motion, climate responds steadily, following the shifting agreement of orbital shape, axial tilt, and timing as they pass through moments of convergence, then drift apart once more. Ice advances with patience, never in a hurry, never announcing its intent. Each winter adds a small contribution, snow compacting into ice that waits to see whether the following summer will undo it. When summers fall short again and again, the balance quietly tilts. Over tens of thousands of years, small advantages accumulate, allowing ice sheets to spread outward from high latitudes, pressing slowly into valleys and across plains. The change feels almost motionless at any given moment, yet persistent enough to reshape continents. This slow growth reflects the way cold works. Cooling tends to reinforce itself gently, helped by reflection, by longer lasting snow, by the gradual lowering of average temperatures. None of these processes demand speed. They depend instead on repetition. Each cycle builds upon the last, and ice thickens only when conditions remain favorable for long stretches. The system resists sudden expansion, requiring sustained agreement among multiple influences before growth becomes widespread. The end of an ice age follows a different rhythm. Warming does not need to rebuild what was lost. It only needs to interrupt the balance. Once summer warmth crosses a subtle boundary, melting begins to outpace accumulation. Ice thins, exposing darker surfaces that absorb more sunlight. This shift changes how energy moves through the landscape, allowing heat to linger where it once glanced away. Feedback accelerates quietly, reinforcing the initial change. At this point, the system responds more quickly. Ice retreats unevenly, breaking into zones of vulnerability. Meltwater flows, lubricating movement and hastening collapse in places already weakened. The transition does not happen in a single leap, yet it unfolds faster than the long buildup that preceded it. What took tens of thousands of years to assemble can unravel in a fraction of that time once key conditions shift. These contrasting speeds arise from thresholds embedded in the climate system. Ice can endure a wide range of cold variations without dramatic change, but it responds sharply once warmth exceeds certain limits. These limits are not fixed lines, but ranges shaped by surface reflectivity, atmospheric circulation, and ocean heat storage. When multiple factors cross those ranges together, change becomes difficult to slow. Tipping points do not announce themselves loudly. They are often reached quietly, recognized only in retrospect through patterns left behind. The climate does not flip states instantly, but once momentum builds in a new direction, reversal becomes harder. Ice that has begun to retreat alters its own environment, reducing the likelihood of regrowth under the same conditions. This asymmetry gives ice ages their characteristic shape: long plateaus of cold punctuated by relatively brief warmings, drawn out in geological records as slow descents and sharper ascents. The pattern reflects the differing nature of accumulation and loss, persistence versus disruption. Through this lens, ice ages appear less mysterious. Their slow arrival honors the need for sustained alignment. Their abrupt endings reveal how sensitive the system becomes Once thresholds are crossed, Earth moves between these states not erratically, but according to the quiet logic of balance, memory, and release. Across the last million years, Earth's climate has traced a pattern that repeats without exact repetition, like a long rhythm played with slight variations. This rhythm appears not in a single place or material, but woven through many records, each capturing a different aspect of the same slow pulse. Together, they reveal a cadence that rises and falls with remarkable consistency. Layers of sediment, coral growth patterns, and chemical signatures preserved in stone all echo this motion. Cold periods return, linger, and then give way to warmer intervals, only for the cycle to begin again. The spacing between these shifts follows a recognizable timing, measured not in centuries but in tens of thousands of years. When these records are aligned, their agreement becomes difficult to ignore. Peaks and valleys appear in step, even when preserved oceans apart or continents away. As understanding deepened, these repeating climate rhythms were compared with calculations of Earth's orbital behavior. The correspondence proved striking. Periods of intensified cold aligned with times when orbital geometry favored reduced summer warmth in high latitudes. Warmer intervals emerged when cycles combined to deliver sunlight more effectively during crucial seasons. The match was not perfect in detail, yet strong enough to confirm a shared underlying driver. What strengthened this conclusion was the convergence of evidence. Geological records derived from independent processes pointed in the same direction. Ocean sediments told one part of the story. Ice archives echoed it. Fossil distributions and ancient shorelines added further confirmation. Each source carried its own uncertainties, yet their shared timing reduced the chance of coincidence. Climate appeared to be responding to a set of slow astronomical rhythms rather than isolated terrestrial events. Over the last million years, the dominant pacing of ice ages also shifted subtly. Earlier cycles followed shorter intervals, while later ones stretched longer, reflecting changes in how Earth's internal feedbacks responded to the same external rhythms. The orbital cycles did not disappear or change their nature. Instead, the planet's response evolved, influenced by growing ice sheets, altered ocean circulation, and accumulated memory within the system. This interplay highlights a key insight. Orbital cycles provide timing, not destiny. They set the stage, but the climate system determines how strongly each cue is answered. When ice sheets grew larger, their inertia altered the rhythm's expression, lengthening cold phases and shaping warmer transitions differently than before. Confirmation came not from a single breakthrough, but from patience. As records improved and extended further back in time, alignment with orbital calculations held firm. Each new data set added resolution, not contradiction. The rhythm remained, steady yet adaptable, present wherever climate left a trace lasting long enough to be preserved. Through this convergence, the last million years revealed themselves as part of a larger continuity. Ice ages did not arrive randomly. They followed a tempo written in motion and light, verified again and again across Earth's archives. The planet's climate, seen through this lens, moves with deliberation, guided by cycles that persist, whether noticed or not, marking time with cold and warmth in enduring sequence. Life does not move in sudden leaps when climate shifts begin. It responds gradually, following the slow rearrangement of temperature, moisture, and season, rather than resisting it outright. As conditions drift, populations adjust their boundaries, expanding where circumstances allow and retreating where they no longer fit. Movement becomes the first answer, a quiet relocation guided by habit and opportunity rather than design. Migration unfolds across generations. Plants disperse seeds toward favorable ground. Animals extend their ranges step by step, tracking familiar climates as they slide across latitudes or climb higher ground. Rivers, coastlines, and corridors shape these movements, channeling life along paths already carved by geography. Change feels less like a disruption and more like a continual search for balance, repeated again and again as climates continue their slow motion. Not all movement succeeds. When shifts outpace the ability to follow, stress accumulates. Specialized species, tied closely to narrow conditions, lose ground first. Food webs strain as relationships fall out of alignment. What once synchronized quietly begins to fray. Extinction does not always arrive dramatically. It often appears as absence, a thinning of presence over time until a lineage fades from the record. These losses are not evenly distributed. Broadly adaptable species tend to persist, reshaping themselves around new ranges and resources. Others depend too closely on disappearing habitats or precise seasonal cues. Their decline reflects a mismatch between inherited strategies and emerging realities. Climate stress leaves fingerprints in fossil layers, marked by sudden gaps in diversity that coincide with periods of rapid environmental change. Yet loss is never the whole story. As climates open new spaces, life fills them. Retreating ice exposes land that has not felt sunlight for ages. Warming seas create new currents and nutrient flows. Into these openings move pioneers, organisms capable of rapid spread and flexible living. Over time, interactions stabilize and new ecosystems assemble themselves from available pieces. These emerging systems often differ from what came before. Familiar groupings reorganize, mixing lineages in unfamiliar combinations. Forests shift their composition. Grasslands replace woodlands. Marine communities reorganize as temperature zones slide. What defines these ecosystems is not novelty alone, but coherence, a new balance formed under altered conditions. Adaptation still plays a role, but it acts slowly. Genetic changes accumulate only when populations remain in place long enough for selection to work. Migration buys time, allowing species to persist while adaptation proceeds quietly in the background. When movement and adaptation fail together, extinction follows. When one succeeds, continuity becomes possible. Across deep time, this pattern repeats. Climate changes set the tempo. Life answers with motion, loss, and renewal, not simultaneously, but in sequence. Each phase leaves traces that shape what follows. The living world remains responsive rather than predictive, adjusting to the shifting stage rather than controlling it. Within these slow exchanges, life persists, not unchanged, but continually rearranged, shaped by climates that never stop moving. Human history began inside motion rather than stillness. Long before villages or memory, early humans lived within climates that shifted slowly but persistently, stretching resources, reshaping landscapes, and altering the paths available for survival. Conditions did not remain fixed long enough to allow comfort. Instead, they oscillated, pressing populations to remain flexible, attentive to change, rather than dependent on permanence. Adaptation unfolded through behavior more than biology. Bodies changed gradually, but daily survival depended on movement, cooperation, and timing. Groups learned to follow water during dry intervals and retreat during advancing cold. Tools diversified, not as a march toward progress, but as responses to variable environments that demanded different solutions at different times. Fire, shelter, and shared knowledge became buffers against unpredictability rather than signs of mastery. As ice expanded and retreated, the geography of migration shifted. Lower sea levels exposed land bridges that connected continents, opening corridors for movement that later vanished beneath rising water. Ice sheets redirected rivers, carved valleys, and formed barriers that guided travel along particular routes. These changes unfolded over thousands of years, yet they shaped where populations could go and how they spread. Human migration followed opportunity as much as intention, tracking habitable zones as climates drifted. When cold intensified, populations clustered in refuges where resources remained accessible. During warmer phases, expansion resumed, carrying languages, tools, and traditions into newly available lands. These rhythms repeated across generations, leaving a patchwork of ancestry shaped by ice margins and shorelines rather than borders. The planet itself organized the pathways of dispersal. Cultural flexibility proved essential. Diets broadened when familiar foods disappeared. Social networks strengthened to support sharing during lean periods. Knowledge became a form of inheritance, passed along to navigate recurring environmental stress. These strategies allowed humans to persist through cycles that favored movement over settlement. Only during relatively stable climatic intervals did a different relationship with land begin to form. When temperatures steadied and seasons grew more predictable, experimentation took root. Wild plants were tended rather than merely gathered. Animals were managed rather than simply hunted. Agriculture did not emerge because climates became easy, but because they paused long enough to allow planning across years. This shift altered human interaction with climate rather than escaping it. Farming tied survival to specific places, increasing vulnerability to future change while enabling population growth and permanence. Settlements flourished under narrow climatic windows that reduced risk just enough to encourage investment in land and structure. These moments of stability were rare within the larger pattern, brief alignments in a restless system. Human evolution therefore unfolded inside climate cycles, not outside them. Movement, adaptation, and innovation followed the slow pulses of ice and warmth. Even the foundations of civilization arose during a calm interval rather than a default state. The story of humanity is inseparable from the climate rhythm that shaped its roots, tested its flexibility, and briefly allowed roots to take hold before motion resumed. Warm intervals arrive quietly and never linger long. Compared to the long, cold spans that bracket them, interglacial periods occupy only narrow slices of time, brief openings where ice retreats, seas rise, and ecosystems expand. They feel expansive while they last, yet within the planet's deeper rhythm they pass quickly, like clearings that appear between dense forests of cold. In these warmer phases, conditions soften enough to allow stability, but not permanence. Ice sheets withdraw toward the poles, exposing ground long held beneath frozen weight. Forests spread into higher latitudes, grasslands widen, and coastlines redraw themselves as meltwater returns to the oceans. Life responds eagerly, filling the available space. Yet the underlying forces that govern climate do not pause. The same motions that allowed warmth to emerge continue to turn. The geological record preserves many such intervals. Each one followed a similar pattern, gradual warming into a peak, then an eventual return toward colder conditions. These endings were not triggered by sudden catastrophes. They unfolded naturally as the slow alignment of cycles shifted again. Summer warmth weakened, ice survived longer each year, and reflective surfaces regained ground. Over time, Cooling reasserted itself without drama, guided by the same patient geometry that had enabled warmth in the first place. What stands out in these records is consistency. Warm periods varied in length and character, yet all remained constrained by narrow bounds. None endured indefinitely. Each represented a temporary balance rather than a new default. The planet did not lock into warmth, it passed through it, then moved on as conditions changed. Within this context, the present climate occupies a similarly narrow window. Temperatures, sea levels, and seasonal patterns align in a way that allows relatively stable coastlines and predictable growing seasons. This alignment supports dense ecosystems and human civilization, yet it exists within limits set by deeper cycles. Small shifts beyond those limits have historically been enough to tip conditions toward cooling or rearrangement. The fragility lies not in imminent collapse, but in sensitivity. Warm periods depend on precise timing and distribution of energy. They persist only while multiple influences remain aligned. When that alignment loosens, change resumes, slowly at first, then with gathering momentum. The system does not resist its own motion. Understanding this fragility reframes warmth as a condition to be understood rather than assumed. Stability is not guaranteed by default. It is a momentary outcome within a larger process that favors movement over rest. The planet's history shows that calm intervals arise, support complexity, then fade as the deeper rhythm continues. Warm periods, then, are not anomalies, but pauses. They allow forests, shorelines, and societies to take shape before motion resumes. The present moment exists within such a pause, defined by boundaries set long before memory. Its calm feels familiar, yet it remains a thin band within a restless system that has never stayed still for long. Change arrives at speeds that living memory cannot hold. The cycles that shape climate unfold across spans far longer than a single lifetime, longer even than recorded history. By the time a full pattern completes, countless generations have come and gone, each experiencing only a narrow slice of the motion. What lies beyond that slice feels abstract, distant, and unreal, not because it is subtle, but because it is slow. Human awareness evolved to track immediate shifts. Day and night, wet and dry, warm and cold seasons mattered for survival. Variations unfolding over thousands of years offered no urgent signal. As a result, perception settles around what repeats reliably within a lifetime. Hills appear permanent, coastlines feel fixed. The climate experienced in childhood becomes an unspoken reference point, assumed to be how the world simply is. This creates a form of generational blindness. Each cohort inherits landscapes already shaped by changes that occurred long before their arrival. Rivers have already shifted their courses. Ice has already retreated or advanced. Forests have already moved. What remains appears stable, not because it has always been so, but because it has not changed noticeably within living memory. Stability becomes an impression rather than a measurement. Slow change rarely announces itself. A few warmer summers blend into memory. A few colder winters feel ordinary. Trends that matter unfold across centuries, not seasons. Without direct comparison to distant pasts, the signal dissolves into background variation. The climate feels constant because the reference frame itself is drifting at nearly the same pace as observation. Even records struggle to counter this illusion. Written history captures moments, not cycles. Oral traditions compress centuries into myth. Only geological archives preserve the full arc, and they require translation before meaning emerges. Until those records are studied and aligned, deep climate remains invisible, its movement masked by scale rather than secrecy. There is also comfort in constancy. Predictability allows planning, agriculture, settlement, and culture to flourish. When conditions repeat year after year, attention turns elsewhere. Climate becomes scenery rather than actor. Its slow motion continues regardless, but it remains unnoticed because nothing forces it into focus. This invisibility does not imply insignificance. On the contrary, the most influential processes are often those that act beneath awareness. By the time their effects become obvious, much of the change has already occurred. Ice sheets do not announce their retreat, one season at a time. Sea levels do not reveal their intent through a single tide. Meaning lies in accumulation. Understanding deep climate, therefore, requires stepping outside daily experience. It asks for patience, comparison, and trust in records that span far beyond memory. When viewed through that lens, the sense of permanence dissolves. What once felt fixed reveals itself as temporary, sustained by coincidence and timing rather than constancy. The cycles remain invisible to daily life not because they are hidden, but because they move at scales the mind was never built to feel. Climate continues its long motion beneath the surface of ordinary experience, steady and unbroken, shaping the world quietly while life, moment by moment, assumes stillness. Not every change in Earth's climate traces back to the sky. The slow cycles described so far offer clarity about timing and rhythm, but they do not claim authorship of every detail. Their strength lies in explanation of recurrence, not in total control. When viewed over long spans, orbital cycles outline when major shifts are likely to occur, setting a tempo that geological records repeatedly confirm. These motions explain why ice ages return with regular spacing, why warm intervals rise and fall within predictable bounds, and why transitions often align across continents and oceans. They account for the pacing of cold and warmth, the broad architecture of glacial history, and the reason climate does not wander randomly through time. The cycles establish a framework within which climate operates, a background rhythm that guides long-term change. What they do not explain are the finer textures layered on top of that rhythm. Orbital geometry cannot specify the exact shape of an ice sheet, the precise speed of a warming transition, or the regional differences that emerge during any given interval. It does not account for volcanic eruptions that briefly darken skies, nor for sudden releases of greenhouse gases from Earth's interior or oceans. These events imprint themselves onto climate, sometimes sharply, without altering the underlying cadence. The cycles also do not dictate outcomes in isolation. They do not force ice to grow or melt by themselves. Instead, they provide conditions under which other processes respond. Ice sheets, oceans, atmosphere, and biosphere all participate, amplifying or softening the signal depending on their current state. A favorable orbital alignment may produce little visible change if feedbacks remain weak. The same alignment can lead to dramatic transformation when feedbacks are primed. Other forces, therefore, matter deeply. Volcanism introduces aerosols and gases that shift temperature on shorter timescales. Ocean circulation redistributes heat, sometimes buffering change, sometimes accelerating it. Ice itself alters reflectivity and elevation, feeding back into the system. Living organisms modify the atmosphere slowly, changing the balance of gases that trap or release heat. These influences interact continuously, shaping how the orbital signal is expressed rather than whether it exists. Understanding climate requires holding all of this together without confusion. Orbital cycles explain the when, not always the how. They describe timing and possibility, not exact manifestation. Other forces fill in the detail, determining magnitude, regional impact, and duration. None contradict the cycles. They operate within the space the cycles provide. Seen this way, orbital motions are neither all powerful nor irrelevant. They are foundational, establishing a long term structure that other processes inhabit. Climate emerges from their interaction, ordered but not rigid, predictable in outline, yet variable in expression. Recognizing what the cycles can and cannot explain allows their role to remain clear, neither overstated nor diminished, as part of a larger system shaped by time, motion, and response. A climate system rarely responds in isolation. When a small change appears, it does not remain small for long, because Earth's components are linked through continuous exchange. Ice, ocean, and air respond to one another in subtle ways, passing influence back and forth until a modest nudge becomes something larger. This cooperation is quiet, but it is constant. Ice is often the first to answer. When cooling allows snow to linger, reflective surfaces expand. More sunlight is returned to space, reducing the energy available to warm land and water. Cooler conditions then favor further ice persistence, strengthening the initial change. The reverse follows just as naturally. When ice thins or retreats, darker surfaces absorb more sunlight, allowing warmth to remain longer. What begins as a slight imbalance in energy is reinforced through repetition. Oceans join this exchange with immense patience. They absorb heat slowly and release it just as gradually, acting as a vast reservoir that moderates short disturbances while amplifying long ones. As surface waters warm or cool, circulation adjusts, redistributing heat between latitudes and depths. These shifts alter wind patterns, cloud formation, and precipitation, drawing the atmosphere into the process. None of this requires abrupt change. It unfolds through persistence. Carbon moves quietly through this system, especially within the oceans. Cold waters draw carbon dioxide from the air more readily, storing it in dissolved form or carrying it into deeper layers. This removal reduces atmospheric greenhouse influence, reinforcing cooling. Warmer waters release carbon back into the air, increasing heat retention and sustaining warmth. The exchange is gradual, but its effect accumulates over time. Biological processes add further texture. Marine organisms incorporate carbon into shells and organic matter, some of which settles to the seafloor. On land, vegetation shifts its extent with climate, altering how much carbon remains stored in soils and biomass. These processes do not act independently. They respond to temperature, circulation, and ice, feeding back into the same system that shaped them. Through these linkages, climate responds less like a switch and more like a network of dials. Turning one influences others, and the combined adjustment moves the system toward a new balance. Small orbital changes, modest shifts in sunlight, or slight alterations in timing can therefore propagate far beyond their initial scale. The planet magnifies coherence. This amplification explains why climate records show pronounced transitions arising from subtle causes. The external push does not need to be large, it needs only to persist long enough for feedbacks to engage. Once they do, the system carries the change forward on its own momentum. Importantly, feedbacks do not create change from nothing. They refine what already exists. They strengthen trends that are supported and dampen those that are not. This selective amplification gives climate its characteristic shape, gradual in onset, decisive once thresholds are crossed. In this way, Earth's climate becomes sensitive without being chaotic. Small nudges matter because the planet listens carefully, allowing ice, oceans, and atmosphere to work together. Through their combined response, tiny variations in energy grow into major shifts, not suddenly, but inevitably, guided by patience and connection rather than force. Testing ideas that unfold across tens of thousands of years requires a different kind of patience. Scientists cannot wait for an ice age to arrive or fade. Instead, they recreate the planet in fragments, assembling its behavior through careful approximation. The work begins not with prediction, but with reconstruction, building confidence step by asking whether the past can be faithfully reproduced. Climate models form one part of this effort. These simulations encode physical laws that govern air, water, ice, and energy. They do not attempt to capture every cloud or eddy. Rather, they focus on large-scale interactions that matter over long spans. When orbital parameters are adjusted within these models, the system responds in ways that can be compared against known climate histories. Patterns of cooling, warming, ice growth, and retreat emerge not because they are programmed, but because the underlying physics allows them. What gives these models weight is restraint. They are not tuned to force agreement with a single dataset. Instead, they are tested against many independent records. When similar patterns appear across different simulations, confidence strengthens. When mismatches arise, assumptions are revisited. The process unfolds slowly, mirroring the subject it studies. Alongside modeling, scientists rely on cross-checking across archives, ice cores, ocean sediments, cave deposits, fossil distributions, and ancient shorelines each preserve climate signals differently. None is complete on its own. When several align in timing and direction, the signal becomes clearer. Agreement across these sources reduces uncertainty, revealing structure beneath noise. This comparison does more than confirm timing. It helps identify where models succeed and where they fall short. Regional differences, delayed responses, and asymmetries in warming and cooling all become opportunities for refinement. Rather than undermining the theory, these details enrich it, showing how orbital pacing interacts with Earth's internal complexity. Confidence did not appear suddenly. It grew gradually as evidence accumulated. Early studies hinted at alignment. Later work extended records further back, improved dating accuracy, and added resolution. Each improvement tightened the correspondence between calculated orbital changes and observed climate responses. The consistency endured across revisions, strengthening trust in the underlying framework. Crucially, confidence also grew through failure. Models that omitted key feedbacks produced incomplete results. Archives that were initially misinterpreted were corrected through better measurement. These corrections did not erase the larger pattern. They sharpened it. Over time, the explanation remained intact while its details matured. Today, the testing continues. New data extends climate records deeper into the past. Computing power allows more nuanced simulations, yet the core approach remains unchanged. Ideas are not accepted because they are elegant, but because they persist under scrutiny from multiple directions. Through this process, orbital climate theory earned its place not as speculation, but as a working description of Earth's deep behavior. Confidence grew because the explanation continued to match reality as understanding expanded. The agreement was not perfect, but it was durable, surviving comparison, correction, and time, much like the cycles it describes. At any given moment, Earth occupies a precise position within motions far larger than calendars or civilizations. The planet continues its measured journey, oriented, tilted, and timed according to cycles that began long before the present surface took shape. This position is not symbolic. It carries real consequences for how sunlight is shared and how climate tends to drift over long spans. Today's orbital configuration places Earth within a familiar warm interval, one that has supported retreating ice and relatively stable coastlines. Distance from the sun, axial tilt, and seasonal timing align in a way that favors moderate conditions rather than rapid glacial growth. This alignment did not appear suddenly. It emerged through gradual shifts that unfolded over tens of thousands of years, easing the planet out of deeper cold and into the narrow band of warmth now experienced. When this moment is placed within a longer view, a broader pattern emerges. Geological records show that before modern times, Earth was trending slowly toward cooler conditions. Ice sheets expanded and contracted, but the overall arc leaned toward growth rather than retreat. This was not a sharp descent. It was a gentle slope shaped by orbital pacing, feedbacks, and accumulation. Warm periods interrupted that tendency without erasing it. The present interval therefore represents a pause rather than a break. It exists within a cycle that has repeatedly returned to cold, then eased again. The planet has occupied similar positions before, each time with slightly different outcomes shaped by background conditions. Ice volume, ocean circulation, and atmospheric composition varied from one interval to the next, altering how the same orbital signals were expressed. Understanding where Earth sits now requires this context. Without it, the present can appear unique or detached. With it, the current climate reveals itself as one chapter within a longer sequence, governed by the same slow mechanics that shaped previous warm periods. The cycles did not end with the last ice retreat. They continue, quietly adjusting timing and distribution of energy. Context also clarifies scale. Changes unfolding across decades or centuries feel significant because they lie within human memory. Against orbital timescales, those same changes occupy a narrow band. This does not diminish their importance. It situates them. Short-term variation unfolds within a framework that operates patiently, indifferent to immediacy. By placing the present within that framework, patterns become easier to interpret. Long-term cooling trends before recent history explain why ice ages remain the dominant state over much of the recent geological past. The current warmth persists because conditions remain aligned, not because the system has settled permanently. That alignment will eventually shift, as it always has, on timescales that exceed ordinary awareness. Knowing where Earth is in its cycle does not predict immediate change. It offers perspective. Climate is not a static backdrop, nor is it an unpredictable storm. It is a moving system, guided by motion and timing. The present moment exists within that motion, balanced delicately between past and future states, shaped by forces still turning overhead. Far beyond immediate horizons, Earth continues along paths already set in motion. The future climate of the planet is not a blank page. It is shaped by orbital changes that can be calculated far in advance, unfolding with the same patience that governed the past. These motions do not rush, nor do they hesitate. They proceed according to geometry and gravity, indifferent to surface events. Over tens of thousands of years, Earth's orbit will continue to stretch and relax. Its tilt will slowly adjust, and its axial orientation will drift. Each of these changes will alter how sunlight is distributed across the planet, not dramatically in any single year, but persistently over long spans. The result is a tendency toward renewed cooling once current alignments soften. Ice sheets respond not to single cold seasons, but to accumulated imbalance, allowing growth when summers lose their intensity. Within this long view, ice ages appear not as anomalies, but as recurring features. They represent the dominant state of Earth's recent geological history, interrupted periodically by shorter warm intervals. The rhythm is uneven, shaped by feedbacks and timing, yet the return of extensive ice has remained a constant outcome across cycles. Future ice ages belong to this same pattern, expected not because of chance, but because the conditions that allowed them before will gradually return. These transitions operate on timescales far beyond civilization. Human societies rise and fall within centuries or millennia, while orbital cycles unfold across tens of thousands of years. Entire cultural histories occupy only narrow bands within a single climatic phase. The slow advance of ice or retreat of coastlines exceeds written memory, giving the impression of permanence where none exists. This does not imply inevitability in detail. The exact shape of future climates will still depend on interactions between oceans, atmosphere, ice, and life itself. Feedbacks will modify outcomes, amplifying some changes and softening others. Volcanic events, biological evolution, and internal dynamics will continue to add complexity, yet the broad outline remains guided by motions already underway. Viewing the future through this lens places present conditions within a longer arc. Warmth does not represent a final state, nor does cooling signal catastrophe. Both are expressions of a living system responding to slow, predictable influences. Earth has navigated these transitions repeatedly, reshaping landscapes, ecosystems, and coastlines in the process. The long view strips climate of urgency without diminishing its significance. It becomes neither threat nor comfort, but motion. The planet moves through states as it always has, guided by light, timing, and response. Civilizations adapt within brief windows, often unaware of the deeper rhythms beneath them. In this perspective, Earth's future climate unfolds quietly, written not in years or generations, but in orbits and angles. Ice ages remain part of the planet's natural rhythm, waiting patiently within paths already traced through space, continuing a story far older and far longer than any moment of human attention. Seeing climate through this lens reshapes scale first, then meaning. Weather once felt local, tied to familiar skies and nearby seasons. Climate felt broader but still grounded, something regional and historical. Now it expands again, revealing itself as a planetary system, responsive not only to oceans and continents, but to motion through space. Earth appears less like an isolated world and more like a participant in a larger choreography. From this view, climate becomes a conversation between planet and orbit. Sunlight arrives not as a constant gift, but as a carefully shaped flow, guided by angles, distances, and timing. Ice, water, air, and life respond together, adjusting over spans too long for momentary perception. The familiar rhythms of seasons and storms remain, but they are carried by deeper currents that operate far beyond geography. Understanding this dissolves the illusion of independence. Earth does not decide its climate alone. It responds continuously to forces that never touch its surface. Gravity, geometry, and motion exert influence without contact, quietly shaping conditions below. The planet listens to changes in orientation and path, translating them into shifting ice, migrating ecosystems, and altered coastlines. This knowledge alters perspective without requiring alarm. It replaces drama with context. Climate change is no longer framed solely as disruption or anomaly. It becomes part of an ongoing process, one that has repeated across immense spans of time. The planet has adjusted before, not through intention, but through response. Each transformation followed naturally from the balance of energy and feedback. At the same time, this view restores humility. Human experience occupies a narrow window within a much longer story. Cities and fields exist briefly against cycles that unfold over tens of thousands of years. What feels permanent now has shifted repeatedly in the past and will shift again. Stability reveals itself as temporary alignment rather than fixed condition. Yet this humility does not diminish human significance, it clarifies it. Civilization developed within a rare interval of relative calm, one shaped by orbital alignment and feedback balance. Recognizing that fragility deepens appreciation for the conditions that made societies possible. It reframes climate not as background scenery, but as an active participant in history. The planetary perspective also softens boundaries. Climate ceases to be something that happens somewhere else, or to someone else. It becomes the shared outcome of Earth's entire system, responding as one. Ice sheets reflect sunlight for the whole planet. Oceans circulate heat without regard for borders. Atmospheric changes wrap the globe evenly. Everything participates. In this understanding, Earth feels less controlled and more alive. Not alive in intention, but in responsiveness. It adjusts continuously, patiently, according to forces that exceed immediacy. There is no final state to reach, no equilibrium to lock in forever. There is only motion, response, and time. Seeing climate this way changes how Earth itself is seen, not as a static home shaped solely by surface events, but as a world in conversation with space, carrying its history in ice and stone, moving steadily through cycles older than memory. The perspective is quiet and humbling, revealing a planet that endures not through resistance, but through adaptation woven deeply into its very motion. Time does not tick here in seconds or years. It turns silently, measured in angles and distance, marking intervals so long they feel motionless. Humanity lives inside one of these intervals, a narrow climatic moment held steady not by permanence, but by alignment. The clock has been moving all along, even as daily life unfolds as if it were still. Civilization arose during an uncommon pause. Fields, roads, and cities took shape under conditions that repeated reliably from one generation to the next. Rivers stayed close to their banks. Seasons returned with familiar timing. Coastlines remained where memory expected them. This regularity allowed planning, storage, and growth, all resting on an assumption of continuity that felt natural. That assumption was never guaranteed. The calm that supported agriculture and settlement did not emerge by design. It arrived through a precise balance of energy, ice, and timing, maintained by forces far beyond human reach. Within that balance, societies expanded, knowledge accumulated, and cultures layered meaning upon landscape. The stability felt like a foundation, but it was closer to a narrow ledge. History recorded triumphs and conflicts, rarely noticing the deeper stillness that made them possible. Climate remained a quiet partner, steady enough to fade from attention. Only in reflection does its role become clear. Stability was not the default state of the planet. It was a fortunate alignment within a much longer rhythm. Above all of this, the clock continues. Earth remains in motion, orbiting, tilting, and reorienting with unbroken patience. These movements do not announce themselves. They apply no pressure that can be felt day to day, yet their influence accumulates, shaping the boundaries within which life adapts and reorganizes. Living inside a moving clock reshapes perspective. The present moment becomes precious not because it is fragile in an emotional sense, but because it is rare in a statistical one. Long stretches of ice and cold dominate Earth's recent past, punctuated by shorter, warm intervals like the one now inhabited. Humanity occupies one such interval, neither first nor last. This awareness alters scale. Achievements that span centuries appear brief against cycles spanning tens of thousands of years. Landscapes, thought eternal, reveal histories of migration and transformation. The quiet forces overhead continue turning, indifferent to names, borders, and calendars, guiding conditions slowly toward their next configuration. Yet life persists within these constraints with remarkable adaptability. Humans respond not by stopping the clock, but by living within its current position. Understanding this does not diminish the present, it deepens it. The world becomes a moment within motion, held gently for now. The clock does not threaten, it turns. Civilization exists within one of its pauses, shaped by rare stability and sustained by it. Above, the forces continue their slow work, not in opposition to life, but as the larger rhythm within which life, briefly and beautifully, finds its place. Nothing ever truly pauses. The cycles described throughout this journey do not conclude, slow, or wait for attention. They continue with the same quiet consistency that has guided Earth through frozen ages and warm interludes alike. Long after individual moments pass, the underlying motions remain, steady and unresolved. Earth keeps responding, whether life notices or not. Sunlight still arrives, shaped by distance and angle. Ice still grows or thins according to accumulated balance. Oceans still absorb, store, and release heat with immense patience. Atmosphere still circulates energy around the globe, linking distant places through invisible flow. None of this requires awareness. The planet responds because it must, because physics and geometry leave no alternative. Life exists within that response, not outside it. Forests shift their boundaries slowly, species migrate, adapt, or fade as conditions drift. Shorelines advance and retreat, leaving marks that stone remembers long after memory is lost. Civilizations rise during favorable alignments and leave traces behind when those alignments soften. Through it all, the cycles persist, indifferent to outcome, generous only in continuity. Seen this way, climate is not a single event or condition. It is an ongoing story written without punctuation. Each chapter blends into the next, shaped by motion rather than decision. Light arrives, ice answers, oceans mediate, and atmosphere carries the result onward. The plot is not dramatic in the moment. Its meaning emerges only through accumulation. This story does not rush. It unfolds at a pace that allows mountains to weather and seas to rearrange. It gives rise to moments of calm and stretches of extremes, neither permanent, neither accidental. Every warm interval carries the echo of cold that came before it. Every cold advance holds the memory of warmth that once shaped the land beneath the ice. Understanding this continuity changes how endings are perceived. There is no final climate state waiting ahead, no destination where motion ceases. There is only passage. Conditions form, persist, and dissolve as alignment shifts. The invisible hands do not steer toward a goal. They simply continue their work, guided by gravity, light, and time. From a human view, this continuity can feel distant. Daily life unfolds on scales too small to register orbital change. Yet the larger rhythm remains present, shaping the envelope within which every moment occurs. Stability feels familiar because it repeats briefly. Change feels sudden because its approach spans generations. In the end, Earth's climate reads like a long sentence written across stone, ice, and water. Words form slowly, erased and rewritten by motion that never stops. Life learns to read fragments of that sentence while living inside it, unaware of how much has already been written and how much remains to come. The invisible hands continue their work without announcement. Earth listens and responds, as it always has. Climate remains a story shaped not by intention or awareness, but by the quiet persistence of motion, light, and time, carrying the planet forward through chapters that never truly end.